It's been a couple of days, a few days I guess, since our last recording, and I do want to continue on with a couple of things. The first of those being the reaction types, and I want to specifically address what I will expect you to be able to do on the test, which is going to be, I'm going to put it available all the way through Saturday. And so let's review over quickly the 5 types of reactions, which I put on the last PowerPoint. The 5 types being synthesis or combination, decomp, which is the opposite of synthesis, single displacement or single replacement, whichever one you like, double replacement, and then combustion. And let's go over an example of each of these super quick. Synthesis, an example of this, if I were to give you hydrogen, and notice that this is diatomic, so you must have the 2 there, plus oxygen gas. Now, I'm not going to put the symbols there because I don't want to clutter things up, but both of these are gases at room temperature. So when they react together to form, to combine, this would be a synthesis reaction, so there's only going to be a single product. That single product, since these are only 2 elements, they can only form one single product, and that one single product is going to be water. And when you write the formula for water, you must make sure that you write the correct formula for water. And when you put hydrogen and oxygen together, hydrogen has a 1+ charge. It's in the group 1A. Oxygen has a -2 charge. So remember, first and foremost, in all of these, that you must focus on writing a correct formula. So the correct formula for this would be H2O. And now, you cannot worry about these charges over here, or these subscripts over here on the left. You cannot worry about this 2 and this 2. They have absolutely nothing to do with these subscripts over here. This subscript 2 on this hydrogen and this subscript 2 on this oxygen is there because that is the correct formula for hydrogen in the gaseous state. When it's by itself, it's diatomic. You've got to have it. If you don't, it's incorrectly written. And yet, why is this 2 on this hydrogen here and there's not a 2 on that oxygen? And it is because of these charges. And you must focus on writing those correct formulas. And we learned the crisscross method. You learn how to write the formulas in chapter 2, I believe it was. You've got to focus on writing those correct formulas. So this is correct. And now how do you take care of that discrepancy that that we don't have the same number of hydrogens and the same number of oxygens on both sides of the equation? Well, you take care of that by balancing. So we have 2 oxygens on the left, but only 1 on the right. So we're going to put a 2. We're going to put a 2 in front here. And now that gives us 4 hydrogens on the right and only 2 on the left. So we also need a 2 in front of here. Now everybody's happy. Now the entire thing is balanced. Now we have a full equation, balanced and good to go. This is what you must do. We completed the reaction, predicted what the products would be, and we balanced it. The next thing would be the opposite of this, which would be a decomp. So if I were to give you the reactants, perhaps I might give you something like sodium chloride, and let's say that it splits apart. Well, this one's easy to do, so what does this split apart to give you? Well, if you're only given 2 elements like this is simple. It's going to split apart into 2 separate elements. Its original elements, sodium and chloride, or chlorine. Now, when chlorine is by itself, it's a Brinkelhoff, it's diatomic, so you must have the little 2 down here because it's diatomic. Sodium does not need the subscript because it is not a diatomic element. It does not have the 2. So this is correctly written, and now we must go through and balance because we have 2 chlorines on the on the product side, and only 1 on the right-hand side. So then we must go through and we must balance and put a 2 in front of here, and that necessitates a 2 in front of the sodium as well. And that is correctly written. This would be a decomposition. So this top one that I wrote would be a synthesis or combination. This second one here is a decomposition, otherwise known as decomp. And then let's do a single replacement. Please keep in mind, you will be required to do some of these on your exam. Remember that single replacements do not always happen, that something must drive them. I believe that I did one of these for you, or as an example, I did a couple of these actually. Let's take your textbook and remind you that in order for these to occur, that you have to have an activity series. Of course, you can look up online an activity series, and you will be given an activity series that you will not be expected to know these. So let's just take, maybe you got some calcium hydroxide. Let's just say calcium hydroxide. And then you have some lithium. Okay. You have to ask yourself, is this going to happen, first of all? And so to find out if this is going to happen, then you're going to look up your trusty handy-dandy activity series. And if you don't happen to have one, you can always look online. And on your activity series, you can see that lithium is not even listed on your activity series, and calcium is the third from the top. So this reaction here is probably not even going to occur. So how do you write that? Remember, you're going to write no reaction, or NR for no reaction. And that's exactly how you're going to record this. So you're going to say, just like so, no reaction. If, on the other hand, this had been, go to a new page, if this had been lithium hydroxide, and then the calcium had been by itself, now this reaction will certainly occur. And say, this one, since calcium is higher than lithium, and we know that because lithium is so low down on the activity series, it's not even listed. Now this is going to happen, but again, you must think about what is the correct formula going to be. Calcium has a positive 2 charge. Hydroxide, you got to think about this as being a single element. It's a polyatomic. It has a negative 1 charge. So this is going to be OH, and you need 2 of them. And then the lithium is going to be all by itself. Now you have to go back again and balance this. And to balance this, we're going to put a 2 in front of here. And that would mean that we'll have to have a 2 in front of here as well. And you see how this would continue. All right? And now let's take on, I want to spend a little bit more time with these double replacements. And I'm going to go to a whole new screen for double replacements. Because double replacements in the Burge book, the book that we're using, it spends the entire chapter nearly talking about the double replacements, because there's lots of different kinds of double replacements. It talks about precipitation reactions. It talks about acid-base reactions. So there's precipitation. This means that one of the products is insoluble. Something has to drive a double replacement. They're not just going to happen randomly, because we talked about in a double replacement reaction that the reactants are going to be 2 ionic compounds, and they're going to be dissolved in water. And in a precipitation reaction, one of the two products is going to be insoluble. And I talked to you about the solubility rules that were in your textbook and that you needed to study those solubility rules. You can get online and Google solubility rules. And there's a list of those solubility rules, and it tells you that if it's a group 1A metal, that all group 1A metals are soluble, and they're going to stay dissolved in water. So if both of your products have group 1A metals in them, like they have lithium and they have sodium and they have those kinds of things in them, well, that reaction's not going to occur. So these would be precipitation reactions if they have an insoluble product, okay? They have an insoluble product. Well, another kind of double replacement reaction, they're called acid-base reactions. Now, acid-base reactions are very common and very important in our personal lives because we have acid in our stomach. We have one of the strongest acids known in our stomachs, and it's used to dissolve our food, and that's hydrochloric acid. And when we have what we call acid indigestion, or we have a little acid reflux or whatever, we eat too much spicy foods, and we take a little Tums or we take a little Rolaids, what we are doing is we are neutralizing that acid. So an acid-base reaction is going to occur this way. We're going to have an acid, which we talked about what acids were. They're going to begin with hydrogen. So let's take the acid that's in our stomach, hydrochloric acid, and let's add it to a base. Let's talk about any base that we want. There are weak bases and there are strong bases. So let's talk about sodium hydrogen carbonate, a relatively weak base. This is baking soda. And this is a way that you can alleviate a tummy ache, sodium hydrogen carbonate. In this acid-base reaction, what happens is, again, our cation ions literally switch places. So this hydrogen is going to come back here, and we're going to get this kind of situation here. We're going to get sodium chloride, which is just plain table salt, and then we're going to get this should be a plus sign. I'm sorry, guys. That was a typo there. H2CO3, which is hydrogen carbonate or carbonic acid. And this then breaks down in our stomachs to give us water and CO2, which is carbon dioxide gas, and this makes us belch, and this alleviates that gas in our tummies. And the rest is just water and salt water, which leaves our body in another way. So there you go. You get a tummy ache, drink you some sodium hydrogen carbonate, a little baking soda mixed with water, and that will help you. It's not going to taste good, but it will do the same thing as Tums or Rolaids if you are in a pinch. This is an acid-base reaction. Now, this one is already balanced. But this is what you need to know about a double replacement reaction. Here's our original two products. They're going to be two reactants and two products here. But in an acid-base reaction, one of those products is going to end up being water. But one of your reactants is always going to be an acid. Remember how we told you it would be an acid. It's going to start with hydrogen. Okay, and one of our eventual end products is going to end up being water. All right, and another kind of double replacement reaction is going to be what's called a redox, an oxidation reduction, where what drives it is a difference in charges, but we're not going to address that. I will take the blame for that. I did allow these lab notebooks and this mix up with the lab kits to just overwhelm me, and was completely inundated with phone calls, emails, and trying to get that problem solved, and I did allow that to interfere with the lecture. So we're going to gloss over the oxidation reduction, and we're going to focus on these two, which are the most important in double replacement. So if it's a precipitation or an acid base. Now, taking those into account, you have to talk about, let's talk about the what drives it, and those are called, there's something called the spectator ions, and then there's what actually drives the ions that are actually involved. So when we're talking about in an acid-base reaction, let's, for example, it is the hydrogen that's involved in the actual reaction, because that's the acid. The hydrogen is what makes an acid, okay? And so in this particular one right here, it is the hydrogen and this hydrogen carbonate which accepts it. This is your base, because the hydrogen is your donor, like a blood donor, only it's a hydrogen donor, and then the base is the hydrogen acceptor, whatever accepts that hydrogen. Well, these are the two that actually drive or force this reaction to happen. The others are just sitting back watching. That sodium and that chloride, they're just sitting back watching. They're called spectators, like fans. They're not on the field playing. So that's what they're called. And so if it's asking you for a spectator, and so if it asks you for the spectator ions, then in this case, the sodium ions and the chloride ions would be spectators, because they are not involved in the actual acid and base portion of this. And the same thing with precipitation reactions. If it's asking you for the net ionic reaction, let's go back and look at precipitation reactions. If you're looking for insoluble products, if it's asking you for the net ionic reaction, it's asking you for what is actually driving the reaction. Let's talk about one like that. Let's talk about another familiar thing, and I did this the other day for you. Let's talk again about sodium chloride, and let's talk about silver nitrate. Okay, if you were to put these two together and I asked you to predict the products, which I will ask you to do, you first must recognize, hey, this is a double replacement. How do I know? I have two compounds that I'm beginning with. There's only one kind of reaction that begins with two compounds, and that's double replacement. No other kind starts with two compounds. So this is a double replacement. What happens in a double replacement? Well, I'm going to take my two cations and I'm going to switch places with them. That means the sodium is going to go with the chloride. The silver is going to go with the chloride, and the sodium is going to go with the nitrate. So I'm going to take this and I'm going to bring it over here. And I'm going to take this. Let me switch colors. And I'm going to take this and I'll put it here with the chloride. Now, you also have to decide what is going to, there's my silver. It has a 1 plus charge, and chloride has a 1 minus charge, so that's the correct formula. And then I have sodium. It has a 1 plus charge, and so does nitrate, NO3. Also has a -1 charge. So this is the correct formula, and it's already balanced. But what drives it? What makes this happen? I'm going to look up my solubility rules, and I'm going to see that silver compounds are insoluble. So this one forms a solid, and it's going to settle out. This is what drives this reaction. So if it asks me for the net ionic reaction, then what forces this to happen? I'm only going to put those ions that are involved in making sodium chloride. What ions are involved in making sodium chloride? Silver. And what's its charge? A 1 plus. And what else? Chloride ions. And what's their charge? A negative. And what do they make together? Silver chloride. And the others, they're staying dissolved. This is a solid, an insoluble solid, so this is my net ionic reaction. All the other stuff is staying dissolved in the water. It's not involved in the reaction at all. They're called spectators. Okay? Alright, and then our fifth type of reaction is combustion, and please keep in mind that a combustion reaction always has the exact same products. So if I were to give you, let's take propane, C3H8 for example, plus O2, you should just be able to look at that and say, oh, that's going to be combustion. I know that because I've got a hydrocarbon there and I've got oxygen, and the products are always going to be the exact same. They're going to be CO2 and H2O. And then you have to balance that, and the trade-off is always going to be the same. These are going to be the easiest to predict the products of, but they're also going to be by far the hardest to balance. Always going to be the hardest to balance. And you always, on hydrocarbons like this, on combustions, you always want to begin with your hydrogens. And if you ever have to put an odd number in front of this hydrogen, you want to double that. So here, I have 8 hydrogens over here, which means I'd need to put a 4 right here. If this was an odd number right here, then I'm going to put a 4 right here. And but if that was an odd one, if I needed to put a 5 right there, I would double that. And then I'm going to put a 3 right here. And that's 6 and 4 makes 10. And the number that you put in front of this lone oxygen is nearly always an odd number. It won't always be, but nearly always. Alright, I'm going to give you some of these to practice. And then we're also going to give you one more PowerPoint, which I'll probably use the PowerPoint from the book for, on molarity, which is concentration of solutions, because we've talked a lot about solutions. These double replacements, they always happen when they're in aqueous solutions. So you've made water solutions, and so it makes sense that we next talk about solubility and how strong solutions are. So that's where we're going next.